here, and I will focus on the adaptations that are needed to do combustion.
Sorry,
yes. Yes. This?
Just somewhere on your
Okay.
in your pocket would be.
Yes.
Sorry about that.
No. Okay, so my specialty is about hydrogen. See? I just. It's okay.
Now it should work. Yeah.
Yes, perfect. Thank you. So specialty is about hydrogen, and in particular, as my title said, hydrogen combustion and safety. So to give you an idea, so I did a PhD on hydrogen combustion, and then I worked for a few years in Ariane Group as a specialist for rocket ignition on hydrogen engines. So we hear a lot about hydrogen transition. And basically what this means is that we're going to reimagine everything for combustionists. So if I'm taking this aircraft as an example, you see that this is not the typical architecture. I mean, outside it looks like an aircraft, but usually the aircraft carries the kerosene in the wings. And here I'm showing a picture from Airbus where you have the tanks in the back. And the reason for that is that the hydrogen takes a lot more volume than kerosene to get the same energy output. It takes less volume than batteries, for instance, but much more than kerosene. So we need to reimagine the whole thing. They're also imagining new, more efficient engines. So this is an example where we basically forget about this outside cap. But basically, this means that we need to reimagine entirely the architecture. And the same holds true for any hydrogen application. So you know that we burn 85% of the world energy comes from burning something, basically, which can be natural gas, oil, coal, which is not very good, but anyway, 85%. So we still have a lot of combustion in the foreseeable future. And if you want to, say, change your combustion chamber from a natural gas combustion chamber to a hydrogen combustion chamber, everything changes. Hydrogen is faster, it has larger flammability limits. Hydrogen is more dangerous and so on. So basically it really, and also when you imagine a combustion chamber, you want it to be able to burn only hydrogen or fully natural gas. And this is really hard. So this is why we need typically new, I mean, we will rely more for this generation of aircraft, of combustion chambers and so on simulations. So don't have to convince you, but I think LBM is a very good candidate. Actually, I think the right candidate to do so. And so I'm going to try to show some results that we obtained with the team. Just so you know, introducing LBM in the combustion community is not very easy. So I'm showing you some of the questions I usually get from the combustion, okay, part. So I'm sure that you're all convinced this is not going to be a problem. Biggest problem is the multi-component part. People don't want to use as many distributions as we need species. Typically, I'm going to show this after, but you can have 10, 20 species that need to be considered. Also, a lot of people in the combustion community say that, of course, the expensive part of their solver is solving, in the end, combustion-related quantities, so diffusion, kinetics, and so on. So even if I divide the cost by 10 for the solver itself, it's not going to make a big difference. This is very common, okay? Not going to comment. And this is maybe more relevant here. So I'll try to maybe show some results and maybe convince you, maybe not. So we'll see with the questions. So usually I start with a first section about basic LBM, but I'm going to skip it here. And I'm going to do a combustion part instead. just to introduce the equations that we need to solve any problem of combustion. I'm sure some of you know, but just in case. So this is the common equation, Navier-Stokes equation, multi-component. So we have mass equation, momentum equation. This is all the same. You're used to this, the total energy equation, and then we have species equation, okay, which looks like that. With this is the diffusion velocity, depends on the model, and this is a stiff source term, which we have for each reaction. Thermodynamic closure, we absolutely need, at the very least, perfect gas closure. So we need to have P equal rho T, okay, but unlike compressible gases, monoconstituent, we have, of course, a dependence both on the temperature for the pressure and also for the species. Here I'm introducing total energy, enthalpy. These are the classical notations for combustion. Keep in mind that for combustion, Cp has to be considered dependent on temperature. It's not constant, and it depends on the species. And this is the transport closure. So this is quite classical. Here we're going to have the stress tensor with a viscosity, molecular viscosity, which is also dependent on the temperature. Turbulent viscosity, if there is one, for turbulent applications. This is the heat diffusion. So we have a contribution of the species. Again, diffusion velocities. This is a correction velocity for, this is a simple model. I'm not going to answer in detail. And in principle, everything is arbitrary and we get from tables. So here, just the main difficulties when it comes to LBM. So of course, we end up with 5 plus NK conservation equations. So this is a lot of equations. For hydrogen, typically 9 equations. So we have 9 species for hydrogen combustion for the detailed chemistry, and that's not included NOx and so on. Large temperature density variations. Of course, dilatable and compressible is not non-negotiable, and variable sound speed is also non-negotiable. Number of equations can be very high, so 20 to hundreds or even to thousands for detailed chemistry mechanism, 1, 2, 3 for reduced mechanism, but you know all these terms are Arrhenius temperature dependent coefficients, so they're very stiff. And for thermodynamic closure, so to mention this, but we have variable Cp. That means that we have variable gamma. This is also mandatory, and we have large molecular weight differences from 2 to for H2 or H1 to typical kerosene, which is going to be 170 or something like this. Finally, transport. Again, this is all arbitrary, so Prent has to be tunable, and usually comes from more complex models. Same for Lewis, especially for hydrogen combustion. Hydrogen has very specific Lewis. Hydrogen is very small molecule, diffuse very fast everywhere, and basically changes entirely the dynamics of the flame. So you need to consider this. Okay, so I'm done with the combustion part. Now I'm giving you the starting point of this investigation. So I work at M2P2. M2P2 is a lab in Marseille, so it's southern France. We're a member of a consortium, which is academic and private, which is called ProLB, which is co-owned by 2 academic labs. So my lab is in Aix-Marseille University and 1 lab in Lyon. And then there are 3 big industrials and CS Group, which does the industrialization of the code. So it's an industrial code. It's not as famous as the one that we saw this morning, I'm sorry, but it's a French smaller version. At M2P2, we're 4 permanent researchers on the topic and 4 research engineers. 2 of them are permanent, and there's a number of PhD students and postdocs. So it's quite an active team. So as I promised, I'm not going to introduce LBM. So I'm only going to give you the basis from where we started with the team. So it's a D3Q19, stands Lattice. The code for now is CPU only, but we have there's a lot of actions in the CS group to carry it to GPU. The equilibrium function is expanded to order 2 or 3 in the classical isothermal version. And the collision kernel, which is used everywhere in the code, is hybrid regularized, recursive regularized collision kernel by Jacob, Malaspinas, and Sago, 2018. I'm putting hybrid into parentheses here because I know a lot. First, because I know a lot of people doesn't like the hybrid part. Maybe you saw Yazon talk this morning, but the hybrid part means that basically there's a ponderation between the second order of equilibrium, which means the stress tensor, and one stress tensor, which is reconstructed by finite volume method or finite difference-like schemes, which adds some viscosity into the model, hyperviscosity. But basically, this is only used in industrial applications. Okay, so in all of the applications that I'm going to show, the academic versions, basically anything that's 2D, we don't use that version. We just use the classical recursive regularized collision kernel. But when it comes to running a full aircraft or a full car or this or that, we use HR. Okay. Again, I'm going to focus on combustion again, but in the lab, my colleagues have different expertise. I'm the only one doing combustion. So some are working on immerse boundary methods. Here we have a big collaboration with the hospital in Marseille to work on fluid structure interaction. We also have collaborations with defense for evacuation problems and pollutant dispersions, atmospheric flows, and so on. But I'm not going to cover this today. So how do we do to compressible and reactive LBM? I mean, this is one option. I know there are plenty of options, but I'm going to present what we did. So the problem was already mentioned several times. There are several problems, of course, but the Lomac problem limit was already mentioned several times. So the several options extend the lattice, which is not the option we followed for several arguments. First is that quite expensive. We have some limitations in terms of gamma and Prandtl, which I said that I'm not happy with for combustion. Even though you can fix that, this is not the option that we followed. And also, but the main argument is that we have too many species. So we would end up with way too many degrees of liberty, in my opinion. So then we have two options. Oops. Okay, doesn't work anymore. So then we have two options. Usually we solve energy and species separately. So a lot of alternatives are available. We can either introduce them in zeroth order of another distribution. We saw this morning under different form. And at the lab, we pursued a simpler, or it depends on how you see it, but a different option, which is to introduce additional equations only as a scalar. Okay, so we're going to have 19 unknowns for the 19 distribution functions, FIs, and then we're going to add one for energy and then one for each scalar. So how do we do this? The idea is that we're going to solve the scalar equation on exactly the same grid, same discretization, so same oak tree mesh. We're going to do an explicit time stepping. So we use the same time step as LBM. And then we're going to, and this is, I hope we can discuss this later, but we do a very, very, very way too simple forward explicit method for integration of the term on the left of each of the equation, and we discretize everything on the right using classical operators, but keeping as much as possible using only the neighbors that are available from the lattice. Okay, so we, as much as possible, apart from some application, we use only the nearest neighbors, because that way, in terms of computing, this is not this is quite easy. So in the first, in our first approaches, we use non-conservative entropy equation for the energy equation and for the combustion applications that I'm going to show, non-conservative enthalpy. And that means neglecting the pressure work. So we only have a dHdt plus u dHdx. Of course, the coupling is very important. I'm going to show this. And any number, in that way, it's very easy to add any number of explicit advection diffusion equation. And this is very useful for combustion because we have a lot of experience from other codes, other methods, which we can transpose very easily. Okay, this is going to be easier. So here is the main algorithm. In the end, it's very similar to the classical LBM. So we compute the equilibrium and non-equilibrium population. We do the collide and stream operation. We update rho and u, okay, from the F, and then at the same time, we compute the updated entropy, for instance, if we consider entropy, using a one-step explicit scheme. So in compressible cases, we use a Mossel-Hancock-like scheme for advection and centered schemes for heat diffusion and viscosity. So that's the simplest we know. And then we do a temperature update using both, we need both rho coming from the LBM part and S or H, for instance, coming from the hybrid part. And then we can update everything. Of course, we changed the definition of the equilibrium. The definition of the equilibrium, the general definition of the equilibrium that we use is like this. So we expand it to fourth order. There are different ways to see it. We can see it as a pressure-based model, as a density-based model, but basically this is all the same. But this, as Ilya said, I think it was the second day, everything is in the third and fourth order, okay? We need to be very careful. Of course, the consistency of the equations is only on the first 0, 1, and second moment, but everything happens in the third and fourth moment. So this is where we need to be very careful. I'm going to illustrate this. So for instance, this is the effect of the fourth order moment. So if we neglect in the previous equation, the fourth order moment, this was typically what we were getting initially from our spherical flame simulations. So you can see that we get spurious currents, which are not spurious anymore, because this is 160 meters per second. And basically, we could not manage to keep a flame circle. And the reason for that, we showed later, is that the force moment is reality. In reality, it allows to put all of the dilatation effect into the static population, F0. In reality, it's in Yazan's presentation this morning, it was written differently. It was written as delta I0 times rho theta or something like this. So this is the effect of the force moment. We need also to be very careful with the third moment. So this is, again, a very simple test case. So this is a jet-like application because we have a lot of jets in hydrogen combustion. So we start with a 2D, this is a 3D simulation, but this is a 2D plane, and we only have a velocity which goes outwards. So it's like a cut of a jet. In which we have a density ratio because there's a change of temperature and there's a jump in velocity. Okay, so it's really like a jet that we cut, and basically we let this evolve for a number of iterations. Okay, and if we use the classical third order, if we don't do anything about the third order, this is known for this 3Q19. For isosomal flows, this one, but basically we get very weird shapes. And of course, this is unacceptable for jets because we would end up with jets with preferential direction eventually. So this is just the message is that we need to be very, very careful about the third and fourth order moments for it to work. So some illustration. This is actually a version that we also developed, which is a low-Mach version. So basically, we rescale it. We use it for large-scale plumes and fires where we don't need the acoustics. Okay, so we rescale the acoustics to keep a reasonable cost. And this was validated over a wide range of applications. So this is a helium plume, typically. So you can imagine that this is the step before we do the hydrogen dispersion into a reactor, for instance. So for this kind of application, what we're interested in is, well, of course, the topology of the flow. I'm not showing here, but also the puffing frequency, which comes from the gravity field. Okay, going back to compressible, these are the first results that we obtained 3-4 years ago on complex geometry. So this is an M6 wing. You can see that the CP profiles agree reasonably with the experiment, but they're not very smooth. They're not very good. So we worked again on this, and this was Yazan's presentation this morning. It's another configuration, but this is a compressible blade cascade, which you can see that we improved a lot the results, the boundary treatment, and the wall loss. Okay, so this is fully compressible. This is total energy. I'm going to get there. This is fully conservative. Otherwise, we would not get the right pressure jump across the blade. So far, I've only talked about non-conservative entropy and enthalpy equations. The reason why this works, and actually I didn't show all of the numerical schemes that we used, but is that we can, but basically it works with almost any scheme, okay, classical scheme. And the reason for that is that the coupling is, in a certain sense, weak. I'm not going to say weak coupling because it's not a mathematical weak coupling sense, okay, but it's weaker than with total energy equation. There's no pressure work. There's no pressure work in entropy equation, and there's no pressure work in enthalpy equation if we neglect it, okay? And this means that we have pure, if we forget about the diffusive effect, we have pure advection equations. And this means that S and H are characteristic of the system. Okay, so we can carry an entropy spot, and you know that the entropy spot is not going to trigger any other mode, any other Kovácsné mode, or any other modes in the Navier-Stokes equation. So this is the reason why it worked reasonably well. But of course, and you'll understand my question from this morning in the previous talk, we don't want to use entropy equation because for compressible applications, basically, we know that entropy equation is correct, of course, on the continuous level, but it's not good on the discrete level, because what's conserved across discontinuities is the flux of enthalpy, not the flux of entropy. Entropy jumps across discontinuities, and so it's a bad choice to use this kind of scheme. And we see it here. So typically, when using entropy equation, entropy scheme, we get the wrong temperature jump in the shock, in the contact discontinuity of the sod shock tube. So we absolutely wanted to go to fully conservative formulations. And the reason why this doesn't work is that we have to pay the price that we do hybrid method. Okay, so we have a different scheme for the enthalpy or the entropy than we have in the LBM. So LBM solves mass, but of course in any conservative equation, the first equation here, there's a mass hidden. If you expand it, you get the mass conservation plus times the scalar plus the density times the non-conservative equation. So if your mass that's hidden in the conservative equation doesn't match exactly that of the LBM, basically we're in trouble. And that's why it explodes immediately. So we developed first model, which is shown here, which basically the idea is to use the same the collide properties, so the fluxes from LBM to reconstruct the flux from the scalar. So you can see it also as if you were to multiply F by phi, typically F would be rho phi, the zeroth moment. So we try to mimic the transport, the advective part, only the advective part of LBM to convect our scalars. So this works pretty well, and this this has the good properties of conserving both the scalar and the square. We recover the Hugonot jump relations. And this works very well. We use this, but it still, it shows no, it's not the best that we found for shocks. I'm going to show right after. So we developed another approach, which basically doesn't build exactly on the LBM flux. So this, because we found basically for really compressible applications, we were getting better results with using muscle, for instance, on entropy equations than this simple centered scheme, which arises from the LBM. So Gauthier Vissok, who's actually a postdoc now here in Zurich, developed a way to build a new numerical scheme to compute the total energy equation and species fluxes, which builds upon any scheme that works basically on the non-conservative form. So we take a non-conservative form scheme. I said basically any scheme works. And then he showed a way to construct the linearly equivalent scheme, but based on the conservative equation. And this makes everything compatible. And basically, we recover the Rankine-Hugonot relationships. So here is the idea. It's quite similar, but basically, we compute the flux with a different, let's take the one on the bottom, for instance. The expected flux is rho uy. Okay, we compute it with the finite difference scheme, and then we have a difference, which is a numerical error in between the flux of LBM, so the flux on rho, which is in reality rho u, okay, which is the one arising from LBM, and the same one computed from the same numerical scheme as enthalpy. So it cancels the error, the mismatch, basically between mass, the mass flux that you have on LBM, and the mass flux that you have in your scheme. And you have to do the same. So for energy, it's a bit more complex because you also have a contribution of the momentum flux in the same way, because the momentum appears in the energy equation via the kinetic energy. So you have two corrections for that one. So once you do this, you can virtually, I mean, if you have a scheme that works for the non-conservative form, it's going to be the same, but with conservative form. So this time we're happy and we can recover all of the classical results for jump relations, shock tubes. These are all a series of 2D shock tubes, which are classical. Okay, so on the left, you see the reference. You see that with the entropy, we get the wrong characteristics, and with the total energy, we get the right results. Okay, now I've introduced the numerical schemes that we're going to use. So as I mentioned, I'm not going to enter in details with all these problems, okay? But hydrogen involves a lot of problems which we're interested in studying. I'm going to focus on a few of them, okay? Turbulent combustion, so this is my next, and combustion instabilities. So the reason why I'm going to focus on combustion instabilities is that LBM is very famous for its properties of acoustic propagation. It's good properties, I would say. And combustion instabilities are a coupling between acoustic waves and the flame. So typically, we're wondering if we would gain anything from using this method. So first, I'm going to show one application, which is a typical application of an aeronautical engine. So this is, you have to imagine the engine I showed earlier is a circle of this combustion chamber, okay? And so there may be 20 of this. This is a smaller combustion chamber which was developed to investigate thermoacoustic instabilities in these chambers, and also to provide the experimentalists and the code developers with a solid reference to validate the codes. So this is what the mesh will look like. Okay, this is a cut of the engine. We have a large plenum. We need to use characteristic boundary conditions. So this is quite classical, and in that case, everything is adiabatic walls for now. But this was early results. Now we can have thermal fluxes and so on. So we have turbulent combustion modeling. We're going to use turbulent Schmidt number, Prandtl number, and we're going to use TF-LES, which is a second flame LES. So this is a turbulent combustion model, basically, which is quite very common in the combustion community. So this is just to illustrate the results on three different meshes. So this is expected. And to get to more quantitative validations, and to show the mesh convergence, I'm showing only this temperature profile. So this is mean on the top on several lines of the burner, and RMS on the bottom. And basically the results that we find compared to other codes. So of course we don't have all of the results, but we get a much more reasonable RMS level at a lower discretization. So here we already get a good RMS level at M1, which is more or less 20 million points. And this is very good compared to other codes. Here we have a discrepancy far from the center, so top and bottom. But this is because in that case, we didn't consider heat losses. This is only adiabatic walls. So this has been corrected since. So going to thermoacoustics now. So again, as I said, thermoacoustic is a coupling between the waves emitted from the flame, typically, which are going to bounce back. So in that case, we used non-reflecting walls, so there's quite few reflections. But anyway, what we want to see is how this acoustic is going to be transported, and it's going to affect back the flame and potentially make an unstable burner. So the first thing, I think you are convinced, but in my community, I had to convince people that I had in the model variable sound speed. So we're using here a simple, very canonical configuration in which we have a flame propagating against a closed wall, the closed canal, and basically the outlet is open to pressure, to atmospheric pressure, and basically the flame is going to start oscillating. Okay, and since the burn gases sound speed is much higher than the fresh gases sound speed, the frequency is going to vary with the position of the flame. Okay, so this is a validation, a canonical validation of the fact that one, we do get the instability of the flame. Okay, this has been simulated many times in the community. And second, that we get the right frequency. That was, I mean, of course necessary, but mandatory to prove to the community. So this is the same burner as I just showed. No, for that burner, as I said, it was developed exactly for this. So there's one configuration for one equivalence ratio. This is methane, which is very steady, quite steady. You see a small pressure oscillation. And if you diminish the equivalence ratio, so you burn with less methane, the flames start pulsating quite strongly. And this is something that we were quite happy to recover with the LBM model. Okay, going to a bit more complex. This was a challenge that was brought to us by a big industrial with a very big burner. So this kind of simulation is very hard to do with typical Navier-Stokes solver, because you have very small details for the injection, which may be a few millimeter holes at the inlet, and you have a 10-meter long burner. You know that the flame is very thin. So what saves us in that case is that we have most of the points you see in most of the points in this region, but since we have a local time step in LBM for free, okay, the small grid points don't cost anything. Okay, and this was very surprising to the combustion community. There are very few codes that do that. There's one code that's actually switching to that. You can only do that, of course, if you have octree structure. So this is a result that we were very happy with. So this is just another illustration. This is a pressure probe in the burner, and the burner is exactly the same in the two cases. We only change the ratio between the methane injection in the center and the flue gas around it. Okay. So you can. So this I think I'm going to skip, but for large combustion, I'm going to very quickly say that for very large combustion chamber, we need to take into account for some combustion chamber, at least not the previous one, but a lot of combustion chambers, we need to take into account radiation. Okay, so we implemented simple radiation models also in the code. So this is a four band P1 model for radiation, which we implemented. I can discuss this later with you if you're interested on how, but we implemented it in the local way, very friendly with the LBM code. So basically, the cost of this is, again, adding 4 scalars. And just so you know, for this kind of burner, this is a typical example. The radiation loss is the radiation power is about 40% of that of the burner. So of course, if you don't take it into account, you're dead. Okay, and for this, we use this to investigate the effect of dilution. Okay, as I said, manufacturer wants gas turbines that can do full natural gas or full hydrogen, because they don't know how much hydrogen they're going to get in the future. So they want to do both, but they know already experimentally and from and also from simulations that the flames are different. So it's very hard to have a design that can accommodate both kind of fuels. Okay, I'm going to just illustrate this last problems because it has a lot of shocks. So here we're also investigating high pressure, so leaks from high pressure tanks. You know that hydrogen, as I said, takes a lot of volume. So basically, either you store it liquid or you store it at high pressure. For cars, typically the option is high pressure. And when I say high pressure, this is 700 bars. Okay, so the gas station is at 900 bars typically. So this is tremendous. So any hole is going to produce a very strong underexpanded jet, something like this. Okay, and so we use also this kind of model. We actually developed also a simple 1D model to do this, but to understand whether this leak just in the contact of air is going to ignite or not. So there are lots of, spoiler alert, basically anything about 300 bars and just at certain hole diameter conditions and so on might ignite just from the contact with the air. And if you have an obstacles, it gets even worse. Okay, I think I have 3 minutes or 2 minutes. Going to finish. This is published, so you can also check the paper, but this is basically the toughest application that we managed to do with the numerical schemes that we developed. So this is detonations. We could validate the ZND profiles, and also I'm not going to enter this in detail, but basically 1D detonations show instabilities which are really hard to capture numerically. And this is an illustration which we recently published of a detonation front propagating. So this one is 2D. This is the one that's 2D. So it's D2Q9, but we're currently putting it into the D3Q19 framework. And you see that depending on the activation, reduced activation energy, so very combustion talk, but we get a very different pattern for the detonation. And this is what explains the cellular structure that experimentalists see on the side of the shock tubes. So we were also very happy with these results, especially considering the limitations of LBM. Okay, so I'm getting to my conclusion. So to me, LBM is a numerical method that's now suitable for reacting flows. We've developed a fully conservative version and a LMNA version, so low Mach number approximation. I usually get the question if it goes beyond Navier-Stokes. For what I did, at least, for what we did with my team, no, I don't think so, because we solved the same equation. Is it worth it? Yes, very much. The cases I've shown you are all in the 10,000 CPU hours. So this is very cheap for these industrial cases. And a local time step is what makes the big difference, okay, in that case. So what's next? We're going to keep working on discontinuities. We already have some on some application on multi-phase flows and radiation. And now I can take some questions. With my 2 ads, I'm going to leave them. Thank you very much.
Do you solve radiation with finite difference, Lattice-Boltzmann, or with gradient?
For now, we solve it with finite difference because I don't know how to solve it otherwise. But if you have I said help needed. So if you have a good idea on how to solve it in a more native way, I'd be interested. So what we did, what we did is cheating. Okay. So I like to cheat, you know, I like to cheat. So you know that of course this is a Poisson equation, Poisson-like equation. So we don't want Poisson equation in our Lattice-Boltzmann code because we lose all of the locality of the solver, of course. But if you look for combustion application, what people typically do for these burners is that they cannot afford compressible. So they do low Mach, it's one thing. And second, they cannot afford to do radiation at every time step. So typically what they do is that they solve the radiation every 10 time steps. So let's say 10 time steps. Okay, and us with the compressible framework, we have a time step which is at least 10 times lower. So what we do here is that we basically do one iteration of Jacobi every time step. We freeze the flow once. We solve the radiation, make sure it's converged. And then that's what we do. And we check that it doesn't go off bound. It works very well. Because in the end, if you have a typical mesh, okay, in 3D, it's going to be on order of 100 or a few hundreds points. So in terms of frequency, and I'm not saying this is satisfactory, but for the combustion community, it's pretty much the same. If you freeze the flow every 100 or 200 or 300 time step, you do the radiation, or you do it coupled, but explicitly, but with a time step which is 200 times slower. This is almost, we don't see the difference.
You do it implicitly where you have finite speed of light.
Sorry?
You have finite speed of light because you're doing it implicitly.
Yeah. No, yes. So I freeze the flow. Okay. If I want to plug in my radiation model, I freeze the flow. I solve it once. I can afford it. I solve it once, and then I do it explicitly one iteration per time step, which is local on the same stencil. If you just do the stupidest way to solve the heat equation, that's how I learned it in school. Stupidest way, you do one iteration, and eventually you converge very slowly, but you don't get too far. I mean, you never get too far. I mean, it's not worse than doing a full precise integration every 200 time steps. This is something that we're investigating. This is what we're doing for now, and this is why it costs us nothing, okay? But this is a trick, it's not satisfactory, but I don't think it's worse than doing it every 200 at a frequency, which is because in the end, again, they do low Mach and they do it every so many iterations. So in terms of frequency of resolving it, it's similar.
Just confirm, so you are solving the Boltzmann-like equation.
Yes. Yes.
Isn't it?
Yes, but I'm solving it explicitly. I'm just doing one iteration per time step, which is again cheating. It's entirely cheating. No, but when I plug it in, I do converge it once, and then I just let the. If I get in trouble, I can do the same as everyone else does: is freeze the flow and resolve it. And you see what I mean? Yes, but if you have a better idea, I'm very open to it because this is a big problem for these industries.
Okay, mal compris. Il a cru que tu faisais une itération à chaque fois et que ça ne convergeait pas. C'est ça. Radiation, pourquoi